Today, we're going to dive into one of the central mysteries of modern computing. We've all got these machines that are supposed to be unbelievably fast, but somehow they can still feel frustratingly slow. So what's the real bottleneck here?
We've all been there, right? You get a brand new, top-of-the-line PC, a super fast processor, but you're still stuck staring at a loading bar. It's this universal frustration, and we're about to unpack exactly why it happens.
Here's the thing you have to understand. The problem usually isn't your CPU. Not really. Think of the CPU as this brilliant, lightning-fast brain. The real bottleneck? Well, it's a massive traffic jam that happens every time that brain tries to get information from the computer's library, its main storage.
And this chart just puts the problem into perfect perspective. Look at this. On one side, you've got the insane speed of the CPU, just crunching billions of operations every second. And on the other side, you have your main storage, which, in comparison, is basically moving at a crawl. This huge gap, this is the fundamental challenge of all computer architecture.
So to bridge this massive speed gap, engineers didn't just build one bridge. No, they built a whole series of them, creating this really clever tiered system of memory. And this entire elegant solution is governed by one single golden rule.
And this is it. This one idea explains everything. It's so simple. The closer memory is to the CPU, the faster it is. But, and it's a big but, there's a catch. That close, fast memory is also much, much smaller and way more expensive to make. So, as you get further away, memory gets bigger and cheaper, but also a lot slower. This trade-off is the key to the entire system.
This rule builds what's called the memory hierarchy, and you can see it laid out perfectly in this pyramid. It starts at the very peak with the absolute fastest memory, the registers, and it flows down to the CPU cache, then to your main RAM, and finally ends at the base with your large, slower storage. Each step away from that CPU represents a trade-off. So let's break down each level.
All right, first up, let's look at the absolute fastest tiers of memory, the ones that are practically part of the CPU itself. This is the inner circle.
So at the very, very top of the hierarchy, you have CPU registers. And they aren't just near the CPU, they are physically built right into it. You can think of them as the CPU's own hands, holding the exact numbers and instructions it's working on at this very instant. There is literally zero travel time.
The next level down is the CPU cache. This is like the CPU's personal high-speed workbench. It's designed to intelligently predict what the CPU is going to need next, so it doesn't have to go very far to get it. It's actually broken into a few levels itself. You've got level 1, or L1, which is the smallest and fastest, for the most immediate tasks. Then L2 is a bit bigger for recently used data, and L3 is the largest, acting as a big shared pool of important data for all of the CPU's cores.
Okay, so moving further down the hierarchy, we get to the types of memory you're probably most familiar with, the computer's main workspace and its long-term archive.
This slide just contrasts the two perfectly. The CPU cache, remember, is the workbench, right there next to the worker, holding only the essential tools for the job at hand. RAM, or main memory, well, that's the entire workshop. It's way larger, holding all the projects you have open, but it takes a short walk to get anything from it.
Every application you're running, every single browser tab you have open, it all lives in your RAM. This is the active workspace. We measure it in gigabytes, so it's massive compared to cache, but it's also significantly slower. And here's the crucial part. RAM is volatile. That means when you turn the power off, poof, everything in it just vanishes.
And finally, we reach the bottom of the pyramid, the archive. This is your solid-state drive or your hard disk drive. It holds all your files permanently, it has a massive capacity, but for the CPU, trying to get data from here is like a crosstown trip. It's a really, really long journey in computing terms.
So we have all these different layers, right? Now let's talk about the magic, the constant, high-speed juggling act that makes your computer actually feel responsive. This latency ladder really shows just how dramatic these speed differences are. It's wild. For the CPU, accessing its own registers is like an instant thought. Grabbing data from the cache, that's like picking up a tool right there on your desk. Going to RAM, that's like a walk to the office kitchen. But fetching something from your main storage drive, that's a trip to a downtown warehouse. It takes thousands, sometimes millions of times longer. So let's walk through a real-world example, something we all get, loading a video game. When you launch it, the game files start way out in the archive, your SSD. They get loaded into the main workshop, your RAM.
As you actually start playing a level, the most important data gets moved right up to the workbench, the CPU cache, and the immediate actions, like your character's movement, are handled instantly by the registers, the tools right in the CPU's hands. It's this beautiful, seamless flow up the hierarchy.
So what this all means is that your computer is constantly and really intelligently predicting what you'll need next. It's always copying data from those slow, large archives up to the fast, small workspaces. This tireless process is what creates the illusion of having one massive, infinitely fast storage system. And that brings us to the final thought, really. Now you know that computer performance isn't just about one component. It's about this clever balance between size, speed, and cost. So for your next upgrade, what's more important for the way you work, a bigger workshop or a faster workbench? It all comes down to understanding the trade-offs. Thanks for tuning in.